Okay, good morning, everyone. Today we'll look at chapter 4. Chapter 4 is transient analysis. This is going to go by quickly. So today I will cover the entire theory and the concepts for chapter 4, and then Monday we'll look at the problems. But the good thing about chapter 4 is there's only one equation in that entire chapter that you need to know. So rather than taking down a lot of notes or looking at all the equations when I go through, I would rather students just take minimal notes, only as much as they need to understand the concepts. Don't worry about writing down all of the equations or the derivations in the middle. As I stated, at the end of the chapter, there is one single equation that works for everything. Okay. All right. So let's go ahead and begin. Now, this chapter is known as transients, and I will explain that in just a couple of slides. Okay, so inductor and capacitors are energy storage devices, right? The energy transfer back and forth into the inductor or capacitor cannot take place in an instant. That transfer requires a certain amount of time. That time required to either receive the energy into the component or discharge it back into the circuit depends on the size of the component as well as the circuit conditions. Basically, the size of the container, the fluid flow, and the size of the pipe, right? So the smaller the size, the faster it fills up or the faster it loses the energy. The bigger the size, the more time it requires. Now, because these are energy storage devices, they all are dependent on time. So one energy storage device requires solving a first order ordinary differential equation. Because it's a first order differential equation, we refer to it as a first order circuit. Okay. Thankfully, greater minds have come before us and have already solved this equation, so we don't have to. Okay. All we have to do is basically recognize a circuit, set up the analysis conditions, extract the information, and then plug it into that standard expression for the solutions. Okay. So that's why I said, we will look at the equations and we look at the circuits, but at the end of it all, there's only one equation we need to understand. All right. Energy is, of course, being transferred back and forth from the inductor and capacitor. When the energy is going into the components or the inductor and capacitor are receiving the energy, we say that they are being charged. Or if they are sending the energy out of the components, then we say they are being discharged. Okay, so energy flows into the inductor and capacitor, we say they are being charged. Energy flows out of those components back into the circuit, we say they are being discharged. Analysis of the circuit during these phases is referred to as transient analysis because the response of the capacitor and the inductor is transient in nature. It is fleeting in nature because after a certain point in time, that response reaches a steady state. Steady state, meaning the value remains constant. It does not change with respect to time. Okay, so that's the reason we call this as transient analysis. So during the transient analysis portion, the energy transfer portion, because it's constantly going back and forth, the response is fleeting. It's transient in nature. And this applies to both DC as well as AC. Okay, we won't look at AC in too much detail until we get to AC analysis. But AC, when you apply an AC signal to a capacitor inductor, there's also a point in time where it reaches steady state. That is a little bit different than, AC, we say, it's constantly changing with respect to time. That's different from this transient analysis. Okay, for this one, we're just looking at generic equations, especially for a DC applied source. Okay, DC voltage and DC current. Transient response for all circuits always follow the same pattern. It is exponential in nature. Okay, it's exponential in nature. Both of these waveforms are showing charging. This one is for voltage, this one is for current. Whether it's voltage or current, it doesn't really matter. Both of them follow an exponential form. A discharging waveform also has an exponential relationship with time. So this is for discharging. Doesn't matter whether it's voltage, doesn't matter whether it's capacitor. If it's charging, it follows an exponential response like this. When it's discharging, it follows the exponential response that I drew on the right. And hence, all we need is one single equation that applies to all circuits. Yes. Current is the rate of flow of charge, meaning the rate at which the electrons are moving and supplying the charge that is flowing through the circuit. Yes. Yep. So let's see, what was I doing? Oh, so yeah, the transient response is the one in the middle. So at the end on the far right, here we see that is described as steady state. Steady state, if you remember from chapter 3, is the point in time where the capacitor or inductor reaches full charge. If it reaches full charge, then the value does not change anymore. It remains constant with respect to time. When it remains constant, it's steady, hence steady state. If it's discharging, at some point in time, it reaches zero. Right? It reaches zero. If it reaches zero, it's still is constant with respect to time. So I like to call it steady state because, again, the value is steady with respect to time. Doesn't change. Okay. But typically, steady state refers to the point where the capacitor or inductor reaches full charge. When it reaches full charge, it has absorbed as much energy as it can, depending on the source, and then it just remains steady with respect to time. Okay. There are two kinds of transient responses, natural and forced. It is not as sinister as the word sounds, right? There's another word, another term that we use is known as the step response. But we still have to, refer to this because this is the standard, standard term that's been used for like decades. Okay, so I still, I would prefer not to use that word, but again, we have to make engineers aware of what it is. Forced simply means you're connecting a source. Okay, you're connecting a source, which is what we have seen so far. We see resistive circuits where we connect a voltage source or a current source. That voltage source or current source is external to the component, right? It's not part of the component. The energy is being supplied externally. That is what we have seen. All circuit analysis where we connect a source is forced response because the response is being forced from the component because of an externally applied energy source. Okay, so again, it has a negative connotation, but it's not as sinister as the word sounds. It's basically charging from an external source is referred to as a forced or step response. And if it has received energy and there is no source connected in the circuit anymore, now it's simply losing the energy out into the circuit, then we call it as a natural response because the voltage or current is simply being naturally drained out. And so discharging of the stored energy is referred to as the natural response. So based on natural and forced, we will look at 4 different circuits, 2 each for the inductor and 2 each for the capacitor. If you have an inductor or capacitor in a circuit, basically we cannot, let's back up. Electric circuits will always have resistors. Resistors are a way of controlling the current, right? If resistor is not present, current is infinite, right? So any electric circuit will always have resistors in the circuit. Now, here you see the natural response circuit simply shows you one inductor, one capacitor connected to one resistor each. Okay, but note that it says EQ. That EQ, as you should be well aware by now, stands for equivalent. Equivalent. So your circuit could have multiple inductors, it could have multiple resistors. But if it is possible to electrically reduce it all down to one single component, we refer to it as one single resistor and one single inductor. And so we refer to this as an RL circuit. RL circuit. Same thing with the capacitor. If you have multiple capacitors in the circuit, and it is possible to reduce those capacitors down to one single capacitor, we refer to it as a RC circuit. Okay, one energy storage device. So it doesn't matter whether physically they might be multiple inductors or multiple capacitors. If they can be reduced to one single energy device, we refer to it as a RL or RC. These single energy storage devices will require a single energy storage device circuits would require a first order differential equation. And because it's a first order differential equation, we refer to these as first order circuits. So one energy storage device physical reduce to one component. Okay, so EQ is just you reduce, sorry, not physically, electrically reduce to one component. Yes. That be a second order. So that was going to be my next point. Yes. So if you have more than one energy storage device in a circuit, like two, for instance, then it would be a second order differential equation. And so it would be known as a second order circuit. Okay, second order circuits second order transient response is a bit more complicated. So, for non-E major classes, I only cover them if we get to the end of the quarter and we have time left. But for now, it's just first order circuits, charging and for discharging. Okay, so these are the step response, the charging circuits. In the charging circuits, we have a source connected. Here on the left, it's a voltage source, so a Thevenin equivalent. And here you have a current source or a Norton equivalent. Okay, Norton equivalent. Let's look at a natural response circuit first. So you have RL circuit, meaning you have one inductor, one resistor in that circuit. If you look at the circuit, the first thing I'd like to point out is the switch. Okay, this is the chapter where we use the concept of switches flipping open and flipping close. Okay, so at time t equal to 0, the arrow is pointing up. It means the switch is being opened at time t equal to 0. So this is an important point. Switch is being opened at time t equal to 0. So your job as an engineer is to set up the circuit. Again, all of the circuits you see in this chapter, you only require one equation. And the equation, you're not solving the equation. Okay, most of the analysis or most of the solution in this is basically understanding what the problem statement is giving you and just extracting information. And that's it. That's like 90% of your solution. So it's theoretical concept that you apply. I wouldn't even call it like electrical engineering circuit analysis. Okay, what you're doing here is you need to logically look at it, understand what it means, and extract information from the problem. So in this case, it tells you that at time t equal to 0, the switch is being flipped open, which means before time t equal to 0, the switch was closed. So time t less than 0, the switch was closed. And if the switch was closed, then the current source IS was connected to that inductor. Eventually, at some point in the past, that inductor had reached full charge. If the problem statement doesn't give you anything about the past, it simply states a very long time, then you simply assume or infer that it has had sufficient time to reach steady state. Okay, it has had sufficient time to reach steady state. We don't care about what happened in the past. We are not analyzing the past. We are not analyzing the circuit before time t equal to 0. But we need to know that value so that we can begin our analysis. Does that make sense? Right? We are beginning our analysis at t equal to 0. So we need to know what the value of that current or voltage is at t equal to 0. For that, we look into the past. That's all. Any questions? Okay. So inductor is a short because it has reached steady state. All of the current is flowing through the inductor. Nothing is flowing through those resistors at all. This allows us to assume that the maximum current is flowing through the inductor, and maximum current should have a value that is equal to that source IS. And that's where we begin our analysis. Okay. Now, at t equal to 0, the switch flips open. If it flips open, the circuit simply reduces to the inductor and the resistor on the right. Everything else is disconnected. So if the source is disconnected and there is no source present in the circuit, it is a natural response. This is an inference or conclusion that you have to make by looking at the circuit. Again, as I said, the analysis in here, you're not writing out equations. It's pretty much, you can, of course, draw out the circuits, but it's the conclusion that you make. What happens before the switch was flipped? What happens after the switch is flipped? After the switch is flipped, it's simply an inductor and a resistor. No source left in the circuit anymore, so it's a natural response. So then you should know which equation you need to use. Okay. We will go over the derivation, and then again, at the end, you will see how that one single equation applies to all. So the initial condition of the inductor depends on the energy that was present in the inductor right before the switch is flipped. This here is an important point. We refer to the beginning of analysis as time t equal to 0. Then there is the concept of t minus and t plus. This simply indicates the time right before. So minus is in the past, so it's right before. And t plus is the time right after. For this class, mostly it's just 0 minus and 0 plus. But E major classes, we look at problems where it's like, t could have any value. 2 seconds, 5 milliseconds. You would say t 5 minus, 5 plus. It simply means the time right before and time right after. It does not have a fixed value. It's simply indicating an instantaneous moment, instant in time, right before the switch is flipped and right after the switch is flipped. And the reason this is important is because the current through an inductor cannot change instantaneously. You cannot snap your fingers and transfer the energy in and out instantaneously. Doesn't matter if you have all 5 infinity stones. You snap your fingers, doesn't work that way. It takes a finite amount of time. So it doesn't change instantaneously. And this allows you to set up your initial conditions. So this is the most important concept. Switch flips. This is the circuit we are analyzing, but we have no idea what the stored energy is. So we have to look into the past to determine that. And the assumption we make is in the past, it was fully charged. Now in the present, it cannot change instantaneously. So it's still carrying that full charge. And we begin our analysis with that assumption. Let's take a pause. Let me know if you have questions. Any questions? Okay. So then we say that the current before and after is exactly the same. I0 is equal to IS. That zero indicates the initial period, time t equal to 0. Sometimes it is also referred to as II, initial. So I stands for initial. Both mean exactly the same thing. That's the point in time that we begin our analysis. Okay. So we begin our analysis, the inductor starts discharging. At this point, we apply KVL at the top. When you apply KVL, we can write VL plus VR equals to 0. You plug in the equations for both the inductor current as well as the resistor current. Resistor current is from IR, Ohm's law. Inductor current is LDI, I'm sorry, inductor voltage is LDI over DT. Resistor voltage is I times R. You have a first order ordinary differential equation. When you solve that equation, this is the form we get. I0 times e raised to minus t over tau. Okay, I of t, the current through the inductor as a function of time can take on any value depending on which moment in time you're talking about. T is the variable, I0 would be the constant, or has a constant fixed value because that's the initial value, the full charge. And then tau is the time constant, L over R. Simply describes the speed at which the energy is being transferred. That's it. Those are the only two quantities in that equation, I0 and tau. Tau would be easy to calculate, not figure out. L would be given to you, R would be given to you. That's the component values. Your job would be to understand the circuit and determine the value of I0. And once you have that, you simply plug it into this equation. As I said, 90% of the solution is simply understanding the problem statement, setting it up correctly, and then simply using the standard equation and plugging the values in. Okay, this is just the first of 4 equations, but you will see they all have a similar structure. And there's be one generic equation at the end to rule them all. Were there 5 infinity stones or 6? Okay, it's been a while. If we have the expression for the voltage or the current, we can find the other quantity by applying Ohm's law. In this case, we obtain an expression for current, right? I of t. Simply apply Ohm's law and we can obtain V of t. So V of t is simply the product. V of t, again, we are talking about the inductor. So the voltage across the inductor will also drop as a function of time. As it loses the energy, the current starts decreasing. The voltage will also start changing. And that would depend on R times I. Instantaneous power, P, is a product of voltage and current. In terms of the resistance, is I squared times R. So you simply plug that into the equation and you obtain this. The total energy dissipated in a resistor would be the total energy that was stored in the inductor, would be half Li squared. That doesn't change. Let's see. RC. Oh, any questions before I go to RC? Same thing here, same concept. You have a capacitor, switch was flipped from A to B. So you analyze the circuit at A, then you analyze the circuit at B. If you look at the circuit at A, capacitor was connected to the voltage source VG. The G subscript simply stands for generator. So the generator voltage that is connected to C capacitor. We are not given anything about the past, simply states it's a long time. So when it's a long time, we simply assume capacitor has reached full charge, steady state. Capacitor voltage VC is equal to VG. That's an assumption that we have to make, or a conclusion that we have to infer. At time t equal to 0, switch flips to the right. When it flips to the right, the left side of the circuit is disconnected. Capacitor is now connected to the R on the right, and it becomes like this. We look at the circuit and we realize there is no source connected in the circuit at all. If it's no source, meaning it's a natural response, capacitor is losing the energy. But what is the value of that energy? We look into the past. When we look into the past, we see that VC is equal to VG, the generator voltage, right? Full charge sometime in the past. From that point on, capacitor behaves like an open circuit. It's steady with respect to time. So it has a value of VG. Then, to analyze, we apply KCL at the top. We get capacitor current IC plus IR equals to 0. Plug in the capacitor current equation. IC is C dV over dt. Current is V over R. Plug in those values. You have a first order differential equation. You solve that, and you obtain the exact same expression, except this time it's for voltage. V of t is V0 into e raised to minus t over tau. Again, only two quantities. V0 voltage, that is the initial value of that capacitor voltage at the beginning of your analysis. V0 or Vi. Okay. Some books, some authors, and some instructors like to use 0, some like to use I. As an engineer, you should understand that both mean exactly the same thing. There is no difference. So if you look at a different, you're sitting in a meeting, you're working, and somebody refers to as Vi or II, that's what they're referring to. Tau, in this case, is R times C. So for a RC circuit, tau is RC, product of the resistor and the capacitor. As straight, as easy as that. Tau is the same whether it's charging or whether it's discharging. So if it's a discharging, tau for a RC circuit is RC. If it's charging, it is still RC. Same thing for the inductor. L over R for charging as well as discharging. Same exact expression. V0 into e raised to minus t over tau. No difference. And that is the reason why we can take one single equation for all four circuits. Okay. Questions? Any questions? Okay, let's look at, standard equations for voltage, power, and energy. Capacitor voltage, we found the equation in the previous slide. So if we have the voltage, then we can find the current using Ohm's law. I is V over R. Power is still V times I. When you plug it into the equation, you can apply V squared divided by R. You obtain an expression for power. And the total energy dissipated in the resistor has to equal the total energy that was stored in the capacitor, half CV square, half CV square. Eventually, all of that energy will be lost. Capacitor voltage will go to 0. Okay, I'm going to skip over this summary slide. Don't actually need it. We look at the step response. Step response are the straightforward. You have a voltage source or a current source, and you connect it directly to the capacitor or the inductor. Inductor capacitor starts charging. There may or may not be an initially stored energy in the capacitor or inductor. For instance, let's say initial energy for the inductor is 0. Then it begins charging. Now it starts discharging again, but before it can discharge all the way to 0, it starts charging again because of a externally applied source. So when it starts charging again, there is some energy that is stored in there. So unless the problem states that the inductor capacitor has been discharged for a very long time, excuse me, you have to take that initial energy into account. Okay. All right. So apply KVL, still the same thing. VL plus VR should equal to some value. Because there is a source present in the circuit, it's not 0, it's equal to Vs. You get a first order equation, you solve that, and you obtain I of t is equal to IF plus I0 minus IF. Now we have an extra quantity in there. Previously, we only had the initial current, I0. Now we also have to account for the final value. Remember the charging expression, right? We start at some value and we reach. So this is 0 or I. This is F, final value. Initial value, final value. So you have to take both into account when you're doing a charging analysis. But the rest of the equation remains the same, e raised to minus t over tau. Okay, e raised to minus t over tau. If the component is completely discharged, if it did not have any stored energy, then I0 would be equal to 0, and the equation would simply be IF minus IF times e raised to minus t over tau. Okay. So no initial energy, then I0 goes to 0. Tau still remains the same, L over R. That does not change. Time constant tau does not change. So again, the equation is exactly the same. It follows the exponential function e raised to minus t over tau. Capacitor, exactly the same thing. You have a voltage that's being applied to the capacitor. It begins charging. You have some initial value of the energy storage. You get a first order differential equation by applying KCL. You solve it. Exactly the same structure. V of t is Vf plus V0 minus Vf e raised to minus t over tau. You have to take the initial energy into account. If initial energy V0 is 0, then the equation becomes Vf minus Vf into e raised to minus t over tau. Time constant still remains the same, R times C. 4 circuits, exactly the same. Let's take a pause before I show you the one grand equation. Let me know if you have any questions. Any questions? Okay. One equation to rule them all. X of t is given by xf plus x0 minus xf into e raised to minus t over tau. Okay. X, let's take it one at a time. X is a variable, could stand for inductor current or capacitor voltage. So it applies for both current as well as for voltage. Okay. XF is the final value. X0 is the initial value. Tau is the time constant. That is again standard, right? Standard expression. So your job is to determine what is the value of tau, what is the value of x0, what is the value of xf. That's it. You find these three quantities, you plug it into the equation, that's your final answer. But 90% of the work, as I said, is finding these three quantities. Tau, again, straightforward. You can find tau if you reduce the circuit. Tau is easy. Then you need to find xf and x0. X0, if it is discharging, If it is discharging, then XF, the final value is, what is the final value? If it's discharging, what is the final value? 0. Always 0. Doesn't matter if the discharge gets interrupted, right? As I said, for E major classes, we solve examples where we state, oh, this fully charged capacitor started discharging, and then before it could discharge fully, we apply external source and it starts charging again. So it never reaches 0. But when we analyze that first stage, XF will still be input as 0. So if it's discharging, XF is always 0. Doesn't matter whether it's capacitor or inductor. Okay. So as soon as you recognize that it's a discharging problem, XF takes on the value of 0. That's it. Now, when it's charging, XF will always equal the voltage or current that's being applied. But there's a caveat, right? You need to find the equivalent circuit to find that final value. And again, I will look at that, I will address that point number 1. So XF, while it is charging, should be equal to the voltage or the current that's being applied. The initial value would depend if the problem statement says capacitor or inductor had some initial charge stored in it, then it would change. But the only standard one value that I would state is that XF is 0 for discharging. So again, XF, X0, and tau. Find those 3 values, plug into this equation, done. XF, X0, and tau. So equation is X of t equals XF plus X0 minus XF e raised to minus t over tau. T is the variable. It can take on any value. And then tau is the time constant. Time constant, of course, is a standard expression, L over R or R times C. Okay, let's address point number 1. Does the equation make sense? As I said, all 4 circuits have the exact same structure. So this one equation rules them all. You don't have to do anything except understand this equation, understand your circuit, and know how to apply that equation, meaning calculate the values and then plug it into the equation. That's it. So point number 1, find the equivalent circuit. What does it mean? You have to set up the circuit for time t less than 0 and then time t greater than 0. So you have to see how the circuit was before it changed and after it changes, right? Before and after. If this was your circuit, you have a resistor and you apply it to a capacitor. This is a random example, so you don't have to draw this out, but think through this with me. What is the voltage VC? Meaning at some point in time, that capacitor is going to reach full charge. What is the value of that full charge? Vs, right? Eventually, that capacitor will reach full charge, Vs, and behave like an open circuit. So your final value in this case, XF, would be the capacitor voltage, which would equal the source voltage, Vs. But what if, so this is R1, this is R1 here, and there is another resistor R2. Now, what is the value of the voltage across that capacitor? Is it equal to Vs? Let me ask that. No, right? It's not equal to Vs because it's not being applied directly. If I redraw that circuit in a way that makes sense, that circuit would look like this. This is R1, this is R2. Capacitor C is in parallel with R2. And then you have your voltage source here. If you remove the capacitor, you know that the 2 resistors are in series. So you have some voltage across R1, you have some voltage across R2, which would eventually be the case when C reaches full charge. because it behaves like an open circuit. But the capacitor voltage in parallel with the R2 resistor will remain exactly the same. But that voltage is not equal to Vs. So you have to find the equivalent circuit by removing the capacitor and analyzing between those open terminals. That's what we mean by finding Thevenin or Norton equivalent circuit, because we have to reduce that circuit down to one single voltage source and one single resistance. So we have to find the Thevenin or the Norton equivalent circuit as seen by the capacitor. You remove the capacitor from your circuit and you analyze it between those open terminals. And that's why Thevenin and Norton equivalent circuits are a very important concept, very important part of circuit analysis. So you find the Thevenin circuit between terminals A and B. Capacitor is removed. Now, for non-E major classes, we are not going to do some large circuits, solving, and then I ask you to find this. But this is a concept. I like to point this out to students because one of the questions is, when am I ever going to use this? When we will ever apply Thevenin? You see right here in chapter 4, how and why it can be important, right? We have to know the voltage that is being applied to that capacitor. We can't do that without finding the equivalent circuit. And that's what I mean by step number 1. When it says find the equivalent circuit, we reduce the components down to one single resistor, one single voltage source. Does that make sense? All right, questions? Yes. So the question being asked is, let's say the switch flips and voltage source Vs now gets connected to R1, R2, and Vc. Is that what you're stating, the circuit conditions? Yes, because the current flowing through R1, R2, and C would depend on the capacitor charging. So the answer is yes. If it's in series, then it would be the same current. If it's in parallel like R2, then again, the voltage across R2 is exactly the same as the voltage across the capacitor. So the capacitor equation applies to R2 also. Yes. Yes. So the question being asked is, would the Thevenin voltage that we find in this example, hypothetical example, would that be equal to XF? The answer is yes, correct. So VTH that we find from here would be equal to the final value. The final value is basically the source voltage that is being applied to the capacitor. And in this case, it would be the Thevenin voltage. Yes. So the question being asked is, in general terms, I think what the question that being asked is, how can we use a capacitor, right? Applications of a capacitor in real life. Am I understanding the question correctly, right? Applications. So one of the most common examples I like to give was in a camera flash. The big ones that are attached on top of a professional camera. If you've ever, have you ever heard like a whining noise in that flash? What is happening is there is a capacitor that's being charged from the batteries. Usually there are like 4 AA batteries, so 6 volts of energy, 6 volts of charge that's supplied to that capacitor. And when you click the camera shutter button, all of that energy stored in the capacitor is released all at once. And so there's a flash light, there's a light bulb that goes off like a flash, hence the name flash. Does that make sense? So there's a capacitor, and when you click on the shutter button, that energy is released all at once. Even closer, everybody uses a capacitor every time you touch your touch screens, because these screens are now capacitive touch screens. When you touch it with a bare skin, it causes a capacitance. I mean, the human skin along with the screen causes a capacitance. That change in that capacitance is detected and is registered as a touch, converted into an electrical signal. Previously, it used to be resistive touchscreens. Resistive touchscreens, you had to apply pressure. So when you applied pressure on it, it would change the resistance value. And depending on the spot where it changes the resistance, that is transferred into an electrical signal. Resistive touchscreens do not work with skin. It requires like a sharp point or a sharp object. Hence, we used to have those styluses to use those, to use those screens. So as I was saying, capacitors, one of that common example is where you store energy that is released all at once. And then, of course, your capacitive touchscreens. Also, there are multiple applications. We look at another application in chapter 6, which is frequency response, which is when we use it for electronic filtering, because the response of a capacitor to an AC circuit is different. Well, not different, but that's where we'll apply. Okay, let's look at the next slide here, where I show a universal time constant chart. Remember, I stated all the examples are exactly the same. All the equations are exactly the same, right? You have e raised to minus t over tau, right? E raised to minus t over tau. Whether it's charging or discharging, this is the only equation you need to understand, because it's e raised to minus t over tau. It's the exponential relationship. This here shows a charging waveform, and this here shows a discharging waveform. Doesn't matter what kind of circuit it is, doesn't matter what kind of value the capacitor inductor has, doesn't matter the value of the resistors. It will always have this exact waveform. That does not change. Okay, that's one of the, for me, it's like one of the mysteries of nature. When we are going into more like philosophy in that sense. How is it that, everything behaves exactly the same way? That's just the property, okay? It has an exponential relationship with time. Whether it's charging, whether it's discharging, it remains exactly the same. In terms of pure numbers, we can plug in values of time to any value we want. 0.01, 0.005, 0.00003, and we can find the value of the voltage or current at any given point in time. But if we plug in the value of time constant as multiples of tau, the time constant, we obtain that universal time constant chart. But look at the first time constant. When it's charging, right, e raised to minus t, e raised to minus 1, e raised to 0, of course, is 1, right? E raised to minus 1 would be 0.32 or 0.368. So when it's charging, what happens is it acquires more than 50%, 63.8% or 63.2% of its charge after the first time constant. So if you look at this chart, you can see that when it's charging, within a very short period of time, meaning the first time constant, it acquires more than half of its charge. Exponential, right? There's an initial burst, and then it kind of slowly flattens out. Discharging, exactly the same thing happens. It loses more than 60% of its charge after the first time constant. So it's a drastic drop, and then it flattens out towards 0. And that's what that equation signifies. So whether it's charging or whether it's discharging, it acquires or it loses more than 60% of the charge or the stored energy. But it's a mathematical expression. So if you plug in a value of t as like 100 seconds, 1,000 seconds, 1,000,000 seconds, or 1,000,000 days, mathematically, you will still obtain some small value of that voltage or current, right? But realistically speaking, after a 5-time constant, it acquires more than 99% of a charge, or it loses more than 99% of its energy. So if it's charging, it's more than 99%. If it's discharging, it's less than 1%. So after 5 time constants, we put an end to it by standard accepted practice, by standard accepted convention. So after 5 time constant, we say it is either fully charged or fully discharged. Okay, fully charged or fully discharged. All right, so Monday, we will look at the example problems. Quiz on Monday is based on chapter 3. Again, I will post an announcement later this afternoon. It'll be on piecewise linear analysis. Okay, I'm letting you know right now, piecewise linear analysis. So you know what you have to study for. And there are a couple of extra solved examples on the website. Okay, it's been there since the beginning of the beginning of the quarter. There is a PDF with solved examples. Go through those examples, go through the examples that are solved in class, and then prepare accordingly. So piecewise linear analysis quiz on Monday. All right, have a good weekend. I will see you all on Monday. Yes.